the previous class, we looked at the preliminary example of how to derive the kinematics of beams, basically relating the 3D strains to the 1D strains, generalized strains, including the force strain measures and the moment strain measures. So what we'll do in the beginning, first 3 slides, is to just summarize that, make certain conclusions based on what we derived as the expressions for the 3D strains. Once we are done with that, we'll get on to a general case where we will relax the ad hoc assumptions that we made regarding the warping field. So we will introduce W2 and W3, which were not there in the previous example, and we will also make W1 a little more general, not as separation of variables where you have part of it which depends only on x1, the other part which depends on x2 and x3. So that's what we intend to do in today's class. So first of all, summarizing what we did with the previous example, we'll just look at the solutions that we got for E11, which is of course the leading term of gamma 11, the extensional strain. Then we will look at the corresponding shear strains as well. So again, we had 2 aspects to it, the small local rotation theory and the moderate local rotation theory. For the class R beams, the local rotations were small, so we had a very simple theory which just gave the 3D strains as the symmetric part of the deformation gradient matrix minus the identity, which is what E is defined as. So each of the EIJ has clear physical significance, and what we look at in this slide is just E11. This is the expression that we derived in the previous class, and if you look at it, this is basically 3D extensional strain, because this is what is the leading term in capital gamma subscript 11, and that in turn contains this small gamma 11, which is nothing but the 1D extensional strain. So there is this difference that you have to observe, that there is a total strain which is a 3-dimensional strain, and then there is this 1-dimensional strain, but this 1-dimensional strain is one of the leading contributors to that corresponding 3D strain. So in other words, capital gamma 11 has this expression and of course the higher order terms, but in this particular expression, one of the important terms is the extensional strain, which is in turn nothing but the extension of the reference curve that you have, because they change in length. So that is basically contributing to that. Then the next 2 terms that you have here, x3 kappa 2 and x2 kappa 3 with the appropriate signs, and of course there is divided by root g in all cases. And that is basically the 3D extensional strain due to the bending in the 2 different directions, about x2 and about x3. And finally, the remaining terms, whatever are there here, are primarily the warping contributions. So the 3D extensional strain due to all the 3 derivatives of the out of plane warping. So in this example, of course, we are dealing only with out of plane warping, W1, but you see that the contributions are there from all the 3 derivatives. For example, this term involves a prime, which means that it's a derivative with respect to x1. This involves a lambda 2, which means it's a derivative of the warping with respect to x2. And again, this is lambda 3 multiplied by xi, means the derivative of w1 with respect to x3. So it basically involves the derivatives of the out of plane warping with respect to each and every one of the 3 spatial directions. All of them contribute. But of course, the contributions of the W1 would be there even in a beam which is not having any initial curvature, that's basically a straight prismatic beam, whereas this particular thing comes in only when there is a pre-twist. So it is a combination of the pre-twist along with the change in warping, out of plane warping with respect to the x2 and x3 directions that basically creates this. But you can clearly see that these are higher order contributions. One fact is that the warping itself is small. How small it is, we'll come to it a little later, though we have speculated upon it earlier as well. But warping itself is small, and in turn you're taking a derivative with respect to x1 that makes it even smaller, because x1 is having an order of magnitude of the length, which is the largest dimension in the beam. On the other hand, these are derivatives with respect to x2 and x3, that's okay. But warping is small, and in turn it is multiplied by the pre-twist, which is also small. So therefore, a product of two small quantities again makes it a much smaller quantity. So in other words, typically the contributions of these terms are smaller compared to the contributions of these terms due to the extension and the bending of the in the one-dimensional sense. So next, let's look at the two terms E12 and E13. Of course, we saw that for that simple example, E22, E23 and E33, these are the strains in the cross-section are all zero, and because of the fact that we assume W2 and W3 to be zero. So the only three strains of interest are basically gamma 11, gamma 12 and gamma 13. So gamma 11 we already looked at. Now we look at gamma 12 and gamma 13, for which E12 and E13 are the leading terms. So the off-diagonal terms E1 alpha are nothing but the three-dimensional shear strains, or the leading contributors to the three-dimensional shear strains. And let's look at those two expressions for E12 and E13. Very similar, just interchange of 2 and 3 and appropriate signs is what makes them different from each other. Otherwise, physical contributions are all the same. So let's look at both of them simultaneously. So one of the contributions is the small gamma 1 alpha term, which basically is the average transverse shear strain, which is the additional rotation that the cross section undergoes over and above the so-called rigid body like rotations, so that it is different from the rotation of the reference curve itself, and that is the reason why it no longer remains perpendicular as it was in the undeformed configurations. That is basically the primary contribution. So once again, it's a direct thing that you can predict, because just like in E11, the first term there was small gamma 11. Similarly, in E12 and E13, the first term is basically the gamma 12 and gamma 13 over there, right? Again, of course, there is this two factor, because we are talking about engineering. We can have a convention for E12 and E13 appropriately. So if you think of E12 and E13 also as in tensorial, then you basically will have a two factor there. If you think of them as engineering, then you would not have the two factors. So that can always be resolved. All that matters is consistency once you have introduced a particular notation. So the next contributor there is, of course, the torsion. So in fact, the torsion would typically be a much larger contributor than even the transverse shear strain in most cases. In other words, this will typically be a leading order term compared to this. This will be a higher order term in most situations. Now, as far as this is concerned, it's basically x2 and x3, the cross-sectional coordinates multiplied by the twist per unit length. And that is basically the shear induced by torsion. So it's very well known, of course, that torsion is resisted within the shaft, or in this case, the generalized concept of beam, by shear stresses and shear strains. Next, we have the contributions because of the out-of-plane warping. And again, this is another part which is pretty well known, because for non-circular cross-section, St. Venant's warping or out-of-plane warping is what is the leading warping, and that is well understood for quite a few cross-sections, even in the non-VAM related literature. So the shear induced by out-of-plane warping and its in-plane derivatives. So again, you see this is basically the out-of-plane warping, which multiplies the total curvature because of the initial curvature and the bending that is there. And so once again, you see that it's a small contribution multiplied by another small contribution. So once again, typically this is small compared to, for example, the contributions from the torsion. Similarly, you have the derivatives of the warping with respect to the cross-sectional coordinates, which is also contributing towards the shear strains, the 3D shear strains of the beam. So let's summarize this whole thing. The analysis, what we did in the previous class, was based solely on two assumptions. In fact, the second was the fallout of the first. The first, of course, is that the maximum strain that you have anywhere within the body amongst all the components of the strain is a small factor, and the other is that the local rotations are not bigger than square root of gamma ij. In other words, the local rotations are small as well. So in the case where it is moderate local rotation, it would be of the order of around square root of gamma ij all the way up to gamma ij. And in situations where like an R class beam, class R beam, there you would have phi k even smaller. Unlike the conventional beam analysis, the removal of higher order terms based on subjective criteria is unnecessary. So it's only these two things which follow from each other. In fact, it's because, as you know, the expression for the 3D strain contains the local rotation, and if the local rotation were much bigger than what we discussed, it's quite obvious that the 3D strain would be larger and would violate the fact that it cannot go beyond the material strain, failure strain values. So leaving that aside, you see that in conventional beam analysis, you will have the removal of higher order terms based on subjective criteria. So that is what is unnecessary here. So typically you would see that you would make certain assumptions based on specific cases, and those kinds of assumptions are not necessary to remove higher order terms. All higher order terms can be boiled down to the problem definition. That is, one is basically the physical small parameter, and the other is of course the fact that it's a beam and therefore the cross-sectional dimension is small compared to the length. The present approach involves fewer assumptions than others, but still the results that you see are fairly simple. So basically contains just the salient features, and when you want to add higher order terms to make it more accurate, you involve the warpings and the local rotations as well. So for classes T or S beams, warping plays a significant role, and therefore you have to go for the little more complex moderate local rotation theory. And that aspect also we have seen, because we derived the whole deformation gradient matrix in mixed basis, and then we saw its antisymmetric part, which is what is the local rotation, and therefore its contribution to the strain in terms of three additional terms involving phi tilde squared as well as products of E with phi tilde, and their contributions also we looked at in the previous class. So with this, we will conclude that example where we had certain ad hoc assumptions. So we'll remove those ad hoc assumptions in terms of the out of plane warping as well as the in plane warping, and then we will we'll be able to deal with all kinds of arbitrary deformations. So the undeformed beam geometry and the derivation of the covariant and contravariant basis vectors are pretty much the same as what we did last time, because there's no difference in that. So let's just rush through that. The reference line, once again, R, is chosen arbitrarily, but it has to be specified. In other words, you have to specify it as either the loci of the centroids or the loci of shear centers, whatever, but that has to be prescribed a priori, because depending on that choice, the meanings of all these 1D variables that we introduced, for example, this small gamma 1, the kappa 1, kappa 2, kappa 3 can change. Okay, so that's the reason why it's important to define that. And depending upon what you're actually trying to find, certain choices of R might be more prudent in terms of making your derivation less complex. So typical cross section is the prescribed domain sigma of a characteristic size A. In the case of class R, there is only one characteristic size associated with it. In an S class, you would have two characteristic sizes associated with that. The material point of the beam in a three-dimensional space is again located by that R hat, which is the position vector, which again is specified first of all by the R, which is the beam axial coordinate x1, which indicates a particular point, and therefore this vector R. And then you have the cross-sectional Cartesian coordinates x2 and x3, which are embedded in the chosen reference cross-section. So you have a reference line, and perpendicular to that, though it is also possible in general to have an oblique cross-section, which, as I said, was useful, for example, in swept wings. But right now let's focus on this. So where you don't have an oblique cross-section, but you have a normal cross-section in the undeformed state, and that is, once that cross-section is chosen, you introduce x2 and x3. Once again, you have the choice. So just like here, R can be chosen arbitrarily. The direction in which you choose x2 and x3 can also be arbitrary, just that they are perpendicular to each other, these coordinate curves because we are talking about a Cartesian coordinate system over here. But again, depending on that choice, a lot of things can change intermediately, though the entire three-dimensional fields that you eventually get will all be the same. But once again, convenience typically dictates. For example, if it's a rectangular cross-section, it will be natural and convenient to use something parallel to the edges as the coordinates x2 and x3. So that's basically embedded in the chosen reference cross-section and therefore valid for other cross-sections as well. Then at each point along R, the orthogonal reference triad BI is introduced. So far we talked about introduction of the Cartesian coordinates x1, x2, x3. Now tangential to these are the unit vectors b1, b2 and b3. So b1 is b2 cross b3, it's tangent to the reference line at all points along R, so therefore it's just obtained as a derivative of R with respect to x1. We've seen that already. And the b alphas are tangential to the Cartesian coordinates x2 and x3 within the cross section. Next, the bi are orthonormal, and therefore unlike the gi's, for example, that we will see later, which is bi dot bj means is equal to the Kronecker delta, and R is the position vector of the reference line points. And if that is the case, then it's quite obvious from this discussion that it means R prime is equal to B1, and all primes, as we have been saying, are derivatives, and when it's a derivative of a vector, it means that the frame in which it is taken is the aircraft fixed frame A. Then the spatial position vector R hat of any cross-sectional point is then obtained using R, and then expanding within the cross-section by using the cross-sectional coordinates x2 and x3 along b2 and b3, and in an initially curved and twisted beam, which is what we are basically dealing with, all of these R as well as b2 and b3 would be functions of x1 in general. So let's next go into the deformed beam. The only difference between this case and the previous case that we saw is the introduction of W2 and W3, and also the fact that W1 need not be written as lambda times xi, where xi is a function of x1 and lambda is a function of x2 and x3. But we will also make an additional change, which again is a choice, it's a set of choice. In the previous case, what we did is we introduced the big B system for the deformed orthonormal triad, where the big B is such that the B1 need not be tangential to the reference curve. So now we will introduce an intermediate reference triad, which is the big T system, T1, T2, T3, in such a way that the T1 is tangential to the reference curve. So it is possible to do the analysis using either B or T. Eventually the 3D fields that you get would be the same, just that one is more convenient to the other depending upon whether you want to lump the transverse shear deformation either in the warping or in the rigid body like motions. That is basically rotations in particular. So that is the only key in deciding that factor, whether you want to use big B or the big T system. So the beam deforms and small bi once again rotates to coincide with the big bi. And B1, as I said, is not necessarily tangent to the deformed beam reference line R, unlike small b1, which is tangential to the undeformed beam reference line small r. So for convenience, we introduce this system T, and just for illustration purposes, we are just showing in a plane where, let's say, big B2 is perpendicular to the screen, and let's say the deformation, again this is not something which will go into the derivations, just for the schematic, just to understand what the difference between the big T and the big B system that we are basically looking at this. Now we are saying that the big B system is like this, big B2 is perpendicular to the screen, and in such a way that all the deformation is taking place within the plane, okay? So that you can visualize this. And then what we are basically saying that is there is a reference curve, and this is the deformed configuration, and B1 in general is not tangential to that, but on the other hand you see that your T1 is defined in such a way that it is tangential to the reference curve at every location, and this is a particular location that we are taking where we are talking about it as the reference cross section. Now you would have B3 along this, but instead you would have T3 perpendicular to T1, because just like the big B system, that big T system is also orthonormal. In other words, all these vectors are mutually perpendicular to each other. Now the difference between what this T3 and B3 is basically your transverse shear. Similarly, when you have a non-planar deformation and the beam comes out of the plane of this screen as well, then you will have the other component of the transverse shear coming into picture as well. So this is what it means. T1 is tangent to R, and the big T alpha, or T2 and T3 in other words, are determined by a rotation about T1 such that you have an orthonormal triad. Now small rotations are there, just like the one shown over here. So basically there are 2 gamma 1,2 and 2 gamma 1,3 due to the transverse shearing deformations, and therefore your big T and big B system would be different in general. If there were a situation where the transverse shear strains were too small or negligible, almost zero, in such a situation obviously Ti and Bi would coincide with each other, or almost coincide with each other. So for small strains, which is what we deal with, because the material cannot take large strains, it fails when there are large strains. So basically it means that for small strains, the relationship between the big T and the big B system can be entirely given in terms of these small rotations which are taking place, which are nothing but the transverse shear strains themselves of in a one-dimensional sense. Somebody has the key, right?
Yeah.
So 2 gamma 1,2 and 2 gamma 1,3. So that's basically the rotations which are involved, and therefore you can see that the big B and the big T system are related in this way. The trivial case is when all the transverse shear strains are zero, and therefore you would see that this matrix would become an identity matrix, or in other words your big B and big T system would be coinciding with each other. So that basically is what this statement literally means. So the reason why they are different is because of the existence of non-zero transverse shearing strains. So the relationship between T and B, or rather their distinction, helps in developing different approximation levels. So one thing is of course convenience in depending upon what you're trying to do and whether you want to lump the transverse shearing deformations gamma 1,2 and gamma 1,3 either in the warping or in the rigid body rotation. That is one aspect. The other aspect is when you're trying to get, let's say, just the zeroth order approximation, or you're trying to get the first order approximation, which is what typically involves for a class R beam the transverse shearing contributions. The transverse shear contributions to the energy are typically small compared to the other contributions like extension, bending and torsion. So when you are using the variation asymptotic method, which is what we'll do in the next class, you will see that it is in the zeroth order approximation you will get only the contributions of extension and the torsion and the two bendings. So when you want to go to the next step, sometimes it's more convenient to use the T system instead of the B system, or the B system instead of T system. So that's something based on the choice of the class of the beam as well as how you want to lump these transverse shearing strain measures.
So,
yeah.
From where this relationship is coming?
Pardon me?
From where this relationship is coming?
Oh, so this is basically a direction cosine matrix that you would use for small rotations. Okay, so you can do it one at a time, and you basically see. So basically, you are taking the sine of the angle to be the angle itself because of the fact that it is small. So small strain. Okay. And later on you will also see when we apply the variation asymptotic method that the order of magnitude of this is not even epsilon hat, but epsilon hat times the cross-sectional dimension divided by the length. So which means that the strain typically is of the order of 1%, and then the cross-sectional dimension divided by the length is, let's say, at least 1/10, which basically means that it becomes almost 1,000th. Okay, so therefore it is not, there is no harm in taking a sine or sine as basic sine of theta as theta itself. So which is how this basically comes. You can do it in a two-step process. You first take only like this, only a rotation about the B2, and then you take only a rotation about B3 of these two angles, and then you have to multiply those two direction cosine matrices. Then you would see that this is what you would actually end up with of course the assumption that sine theta tends to theta and cos theta tends to 1 minus whatever. So
sure.
Yeah.
This is valid for both small strain and small rotations.
That's correct, yeah. So, because these two things are related, they're not that they are independent of each other, because once you have limited your strain, because the strain depends on the local rotation, therefore the local rotation cannot be much bigger than a particular value, otherwise it would make the strain larger than the material failure strain. So next, let's continue with the geometry of the deformed configuration. R is the position vector to the point on the new reference curve that you have in the deformed configuration, which is big R. And Wi would again be the warping measured numbers along Bi, irrespective of whether you're doing it in the big T system or the big B system that you're using with respect to the deformed configuration. In both cases, remember that the warping components W1, W2, W3 is an expansion of the vector W over the small b system. So that's how we have defined it. So it remains the same, and it is prior to this rotation from the small b to the big T system, which is the rigid body like rotation, which is contained within this finite rotation tensor dyadic over here. Okay, now this fact means that the position vector in the deformed beam of the particle with the position vector r hat in the undeformed beam is basically given by this. So big R hat will be given by R of x1 plus x alpha. Remember in the previous example we had taken this as big B alpha, and then Wi we had taken along big Bi. Now we are taking it along Ti. But now note that all that this r hat is doing is it's mapping a point which was at small r hat to a particular point in the deformed configuration. So that should be blind to my choice of whether I take a big T system or big B system. A particular material point moves to another particular point, and that vector is fixed irrespective of whether I choose to model it using big T's or big B's. So in other words, your r hat should be the same, your r is the same, but basically it is this term which we were earlier calling as x alpha b alpha, and Wi Bi is now instead written as T alpha in terms of the T system, but we know that in general the T system is different. So how is that possible that this r hat and the r hat that we defined in the previous class are one and the same? The solution to that is the fact that the Wi now has a different meaning. Okay, in other words, the Wi that you had in the previous case and the Wi that you have here are having a slightly different meaning because of the way the transverse shear strain is being considered. In one case it is being considered with the rigid body rotation, the other case it is being considered with the warping, which is what we are doing now. So just recap that T1 is chosen as tangent to R, so that is basically to this reference curve in the deformed configuration. And the transverse shear deformation here is classified as part of the warping field, whereas in the previous case it was part of the rigid body like rotation. So with that, keeping that difference in Wi in mind, this is still valid. So strictly speaking, for example, I would have had to use a different variable here to denote that this Wi is not the same as the Wi I used in the previous class, but just that there are two different examples. So I can introduce a new meaning to Wi over here and call this Wi such that it is warping, but it includes the transverse shear deformation within itself. So the small strain assumption that we are making because of the materials that we are limiting this discussion to means that the classification neither introduces additional approximations nor an information loss. So this classification of where you put the transverse shear deformation, like in the previous case into the rigid body rotations, or in this case where we are using the big T system into the warping field, in both these cases the eventual 3D results would be one and the same. So in other words, there is no information loss, or neither is an additional approximation being used here or in the previous example as far as this aspect is concerned. In other words, your 3D field is going to be one and the same, just the way you are breaking it up into two parts, let's say A plus B, is different. So instead of A1 plus B1, you are breaking it up into A2 plus B2 in a different way, but the sum remains the same. So that is basically your total 3D contribution remains the same, just a matter of convenience in two different cases for two different goals. So typically your gamma 1 alpha, as I said, will be of the order of epsilon hat A by L. This we still don't know, but that's something to be proved by the application of the variation asymptotic method, which we will see later. So what it means though is that that result which we eventually get is that it is one order higher than the other 1D strains that we already introduced, which is basically the classical 1D strain measures. And of course in this case, because we are lumping the transverse shear into the warping, we cannot treat it as a 1D variable like we did in the previous case. We had 6 1D variables. 3 were the force strain measures and 3 were the moment strain measures. The 3 moment strain measures remain in this case as well, but the 3 force strain measures you had, that is gamma 11, 2 gamma 12 and 2 gamma 13, all small gammas. Out of that only gamma 11 remains. The gamma 12 and gamma 13 are no longer 1D strains. They have been put into the 3D field, which is the warping, even though they are actually functions only of x1. So that's what we have, and so what remains is just 4 terms, only one quantity which is a force strain and the other 3 which are the moment strain, just as in the previous case. So these 4 are called as the classical 1D strain measures, and they are in turn related to the 1D strain measures that we defined in the previous class, which are basically the ones without the bars. That they are taken under the special case that gamma 1 alpha is set to 0 here, so that it is in turn going into the warping and therefore appears in this term to get the same position vector r hat, big R hat as before. So this is recap, shows that the general class strains of the classical theory are these: the extension per unit length of the reference curve, the twist per unit length again at the cross-sectional level as a whole on an average, and then again the 2 bending curvatures of the reference curve as different from the initial curvatures that you had. So this is not the big K, but the big K, K2 and K3 minus the small K2 and K3. So now here of course small k1 is the pre-twist rate and small k alpha are the initial curvatures, and we have this very useful relationship to bring in the initial twist and curvature into the formulation, that when we calculate the covariant basis vectors for the undeformed configuration on the pathway to calculating its quantavariant basis vectors as well, we need the derivative with respect to x1 of all the unit vectors there, and there we bring in this by this definition again analogous to the angular velocity definition. So kj times bj crossed with bi and an implied summation over j, so that you basically end up with the bi prime. Now, consistent with geometrically exact definitions, the moment strain measures kappa I bar, again repeating the definition we had at the end of the last slide, are nothing but the same as kappa I, just that you're setting the gamma 1 alpha here equal to 0 so that you push it into the warping, and that's basically what is kappa I bar. So you would have a very similar definition compared to what you have in the undeformed configuration. Now in the deformed configuration, so in the deformed configuration, instead of the small b's, you now have the big T's, and instead of the k, small k, you have the big K, which is now the small k plus the kappa, okay? And this kappa is no longer the same as before, but the kappa bar, which is under the condition that gamma 1 alpha equal to 0. So that is basically what you have here. And again, you might recollect in the previous example, we had a similar relationship where we said that big bi prime is equal to small kj plus kappa j, which was this kappa j, and again big bj crossed with big bi. So we're just replacing the big b's by the big t's, and we are replacing the kappa by the kappa bars over here, and the equation remains one and the same. So defined based on changes along x1 of the frame T consisting of this triad T1, T2 and T3. The choice of this triad, how you choose T1, T2, T3 implies that the 1D force strain measures associated with 0 shear deformation, leaving only extensional force strain, which is gamma 11 bar. So in other words, 2 gamma 12 and 2 gamma 13 are taken as 0 because they are supposed to be included in warping. So it's not that we are making an additional assumption. So once again, I'm stressing that fact. It's just that the location where you are considering it is different. So therefore, here you don't need to deal with those two strain measures. You are treating them as if they were zero. You know very well that warping will take care of it. So to consider the case where gamma 1 alpha is not equal to 0, another set of moment strain measures associated with the big bases introduced earlier. So this, as I said, was the equivalent, and this is what we used in the previous example. We will not use it, but just to show you the parallel and the difference between the kappa variable that we had chosen previously and what we are choosing over here now. And it can be proved by the geometry, and you can see that in the textbook as well, that even in the case where you have the whatever the general deformations might be, whatever the variables which are non-zero, in all general cases you would see that even though gamma 11 bar is defined as gamma 11 when 2 gamma 1 alpha are set equal to 0, even when they are not 0, it turns out that you can prove that gamma 11 bar is nothing but the same as the gamma 11 that you used previously in the previous example. On the other hand, the kappa 1 bars are in general different from the kappas, and what they are different by is of course dictated by the non-zero values of your gamma 1 alpha, and that basically means that the change in gamma 1 alpha with respect to the x1. So it's gamma 1 3 prime and gamma 1 2 prime, which is what is the leading change to the kappas in determining the kappa bars. So already we saw that the gamma is very small, the gamma 1 3 and gamma 1 2, they are of the order of epsilon hat times A by L, okay, where A is the cross-sectional dimension order and L is the order of magnitude of the wavelength of deformation along the length of the beam. So it's typically of the order of 10 power minus 3, gamma itself. That you are taking a further derivative with respect to x1, which is again a long length, which is the longer dimension of the beam, and therefore you see that the actual difference that basically these contribute to the kappas in determining the kappa bars are indeed very small. So this is all that is there if you have an initial prismatic beam, so that is basically no initial twists and curvature. Once you bring in the initial twists and curvatures, there is a further difference. The initial twist causes the difference in the bending curvatures, and on the other hand the initial curvatures cause a difference in the twist per unit length. So it's basically the roles are reversed, but basically again it is driven by the transverse shear strains. So this is basically the relationship between the two different ways of defining these quantities, and it's quite clear that for the leading order terms this may not make much of a difference. In any case, the transverse shear strain is not something which appears in the leading or so-called zeroth order approximation. It's a higher order quantity which comes in the first order approximation. Next, your r hat is an important thing to see, that basically how do you determine r hat? R hat is a vector, so like any other vector, it basically has three quantities along three different directions as the measure numbers, and once you know those three quantities you would be able to determine it. So in other words, you had a undeformed beam, you are monitoring just one particular material point in this beam, somewhere along the length, somewhere in that particular cross section, and now after the deformation it has gone somewhere else. The number of quantities you need to determine that motion is just 3, okay, because in 3 different directions how much it has moved by. But instead of that, what are we doing? We are having 7 quantities. 4 are the classical strain measures, gamma 11 bar, kappa 1 bar, kappa 2 bar, kappa 3 bar. In addition, you have the warping W1, W2, W3. So total of 4 plus 3, you have 7 quantities. So in other words, though just 3 quantities were necessary, the measure numbers of r hat, instead we have brought in 4 epsilon bars and the 3 wi's, a total of 7. So 7 minus 3, we have an order of redundancy of 4. So in other words, we have to bring in 4 additional equations in order to solve this problem, and that's where the constraints will come into picture on how you constrain these wi to give a specific meaning to the epsilon j bars, or in other words to what epsilon j bars are in terms of the rigid body translations and rotations, that is basically the u's and thetas. So that's what we will do in a couple of slides later. We will see that we will derive those 4 constraints. Again, there is no unique way or sacrosanct way that these constraints have to be developed. Depending upon how you develop them, it gives certain meanings not only to the warping, because these constraints are on the warping, but it also gives certain meanings to the other quantity that you have, which is the set, which is now defining where an arbitrary material point goes. So once you define those constraints, it gives in particular a specific meaning to what these epsilon j bars are, and in turn to what the ui's and theta i's are. So let's look at the deformation gradient matrix measure numbers in the mixed basis. So using big TI instead of big BI. So that's again something which we did last class using the big BI. The only difference is now we look at it with the big TI. So we'll not go into the full details of it. I will just go through a summary of it. So just let's remember that the decomposition of the rotation tensor is what introduced us to the Jaumann-Biokashi strain measure numbers for the small local rotation as this in terms of the leading terms, because this is what is EIJ in the right hand side over here, and we saw that in the case of the small local rotation with theory, which is valid for class R beams and for class S beams when there is no axial load, for example. Or some other special stringent cases for the others, but for class R beams always. So that's basically what it is, the symmetric portion of the deformation gradient matrix minus the identity matrix. But now with the chi ij defined in a different way. Okay, so in other words, there you had still defined the deformation gradient tensor the same way, that is big GK and small gk juxtaposed with each other, but the way you expanded it out was with respect to the small b and the big B system. Instead of the big B system, now you have the big T system that you have, and so your chi is expanded once again in a mixed basis, but the choice for the deformed configuration, the Cartesian triad that we have, is now instead the big TI system. So your chi ij will be slightly different because of this particular thing. That is, you have the TI over there. So 3 types of base vectors are needed above, defined as before once again. So again, you need the covariant base vectors in the undeformed configuration found by the derivatives of the position vector with respect to the corresponding cross-sectional coordinates. Then you have perpendicular to those surfaces formed by pairs of the covariant basis vectors is the contravariant basis vector, just determined by the cross products, and of course the metric tensor's determinant comes into picture as well. Determinant gm dot gn, determinant of the undeformed geometry's metric tensor expressed in the small b system to get the matrix and then its determinant. Then basically your gi, that is the covariant basis vectors for the deformed configuration, that is the uppercase gi, are determined just similar to this. Instead of the small r hat, you have the big r hat. And once again, you take the differentiation with respect to the 3 cross-sectional coordinates. In both cases, the differentiations are with respect to the frame A. Now we estimate the order of magnitude of the warping. This is another thing which is kind of a prerequisite before we go on and apply the variational asymptotic method, that we have to have an estimate of the orders of magnitude of not only the known quantities but also the unknown quantities based on certain problem definition parameters. In this case, what helps us to determine the order of magnitude of the warping is basically the fact that the strain is small. So if the strain is small, the warping cannot be beyond a particular size. If it is beyond a particular size, once again it would violate the fact that the strain is small. So this is similar to the kind of argument we had, for example, with the local rotation. Same thing holds with respect to the warpings as well. So how do we go about estimating the orders of magnitude of the warping? Now, of course, the basic premise for it, as I said, is the fact that the maximum strain amongst all the components anywhere in the beam, again throughout the interval under consideration for a dynamic problem, is of the order of quantity which we shall denote as epsilon hat, just as in the previous classes. So gamma ij, some of the gamma ij's, the components gamma ij, when you expand out, you would see that irrespective of whether the definition is using the big B's or the big T system, you would see that it contains terms like the derivative of a particular warping measure number Wk with respect to x alpha. So it has these kinds of derivatives where alpha is between 2 and 3 and k is varying between 1, 2 and 3. Of course, you would have derivatives with respect to x1 as well, but our focus is on these terms, that is derivatives of w1, w2, w3 with respect to x2 and x3 only, the cross-sectional coordinates only. Now these are terms which are always present, whether you use the big T system or the big B system. You would see when you expand out the gammas, you would get these as quantities on which gamma ij depend. In particular, the gammas would be gamma 2, 2, gamma 3, 3, gamma 2, 3. Those are the places where you would find the things that we typically need. And of course, gamma 1, 3, 2 in order to determine the W1 as well. So what that means is that because that is one of the terms there, that term cannot become bigger than the strain, otherwise its contribution to the strain will be very large, and therefore the strain itself will become large, and therefore those kinds of terms should also be of the order of the strain itself, which is order of epsilon hat. Now we know the order of x alpha, which is basically the cross-sectional dimension, and therefore from that you can determine the orders of each of the W's. So in the case of class R beams, again now there will be a difference depending upon whether you're considering class R beams or on the one hand, or the class S and class T on the other hand. So if you are talking about class R, which is the simplest case, the regular beams, then there is only one characteristic dimension in the cross section, which is denoted by A. For example, it could be a square cross section with width B and height h, where B and h are both of the order of magnitude A. So x alpha is of the order A, which basically means that your Wk is of the order of epsilon hat times A. So that's how we end up estimating the order of magnitude, but remember that it is only an estimate, okay? It's not the actual order of magnitude of W hat necessarily. It's only when you actually find a solution for W and then you see what is the expression for it. It will be in terms of known quantities whose orders of magnitude you already know, and therefore then you can come back and check whether whatever order of magnitude you estimated is correct or not. So that self-check procedure is possible within this procedure. So subsequent warping solution, when we get it, after applying the variation asymptotic method, which we will do in a couple of classes later. So then we will see that the subsequent warping solution will show that all the terms that you get in a large expression for the WKs will be such that each of those terms, at least the leading terms of that, will all be of the order of epsilon hat A, and of course the other terms would be higher order compared to this, which still does not violate this particular fact. So that this estimation indeed is correct. So the product of warping and 1D generalized strains are also present in the 3D strain field. So amongst the many terms that are there in gamma ij, some are like this. The other, which are derivatives of the warping with respect to the cross-sectional coordinates. There are also certain terms which are, let's say, derivatives of the warping with respect to x1. It's quite clear that if this is the order of Wk, then the derivative with respect to x1, which is like a Wk prime, is nothing but epsilon hat A divided by L, because x1 is of the order of magnitude of the length of the beam, and A by L is a small parameter, so you can see that that is basically a smaller contribution to the strain, so typically higher order contributions to the gamma ijs. Apart from that, you will also see in the expansion of gamma, once again, irrespective of whether you have used the big B or big T system, when you have the full expressions for the capital gamma, then you will see that some of those terms not only involve purely warping, but also products of the warping W's with the 1D generalized strain, say W multiplied with a kappa 1 or W2 multiplied with let's say a kappa 2 or kappa 3, etc. So you will have products of warping and the 1D generalized strains in many of the terms of big gamma ij. So now that it's quite clear that if warping itself is of the order of epsilon hat A and the 1D generalized strains, when appropriately non-dimensionalized, are of the order of epsilon hat, the product of them will become epsilon hat squared times A, and of course the appropriate derivative will be there, and therefore it will typically be of the order of epsilon hat squared contribution to the gamma ij, and so you would see that those can be neglected as well. that said and done, it's always in the variation asymptotic method, the right place to do the dropping off of higher order terms is not the strain but the strain energy, because or rather more specifically the total potential. Okay, so that's where the dropping off of the higher order terms should happen. But in situations where, let us say, the stiffness matrix, the 3D stiffness matrix has all terms of the same order of magnitude, then irrespective of whether you do the dropping off of terms at the strain energy or at the strain is one and the same. They are equivalent to each other, because the strain energy is defined as a quadratic in the strains multiplied with the stiffness, 3D stiffness matrix. So in many cases it is more convenient to drop off in such examples where all the stiffness matrix terms are of the same order of magnitude. In such situations, we can drop off the higher order terms in the strain itself rather than multiplying with the stiffness matrix and then again making it quadratic in the strains and then expanding it out and then looking for the higher order terms to drop out. So on the other hand, this discussion so far was for the class R beams. The case of class T and class S is a little more complicated because local rotation comes into picture. It's no longer small, it could be moderate, and as we saw in the previous class, why it is moderate not rather than small. In other words, it's bigger than the strain in terms of size. So the nonlinear terms in gamma ij would then occur because of the fact that local rotation enters into picture. We saw in the expression for gamma ij, we had a leading term which was eij, and then you had terms like phi tilde squared, we had terms for phi tilde multiplying e. So it's quite obvious that all of these will involve products of the unknown quantities and therefore nonlinear terms in gamma ij, that is in the 3D strain. And many of those nonlinear terms will not be discardable, including some of these products that we just talked about, namely the warping times the 1D generalized strain, because those warping terms would appear as local rotations, because the derivative of the warping with respect to the cross-sectional coordinates or with respect to x1 turns out to be the local rotations, and therefore their product with the 1D generalized strain, when they are moderate local rotations, may be something that we have to take into consideration. If we don't, we will not be able to capture the kind of effects that we talked about, the nonlinear cross-sectional effects like the trapeze effect and or the brazier effect.
Sir, in case we have estimated the order of warping wrongly, so then we have to, by substituting the correct order again, we have to do an analysis again?
That's correct.
Or is with whatever we have assumed the solution that we have obtained, is it correct?
See, what would happen is, if at all you get a solution for warping which is different from this, there are two options, right? One is it is bigger than this, one is it is smaller than this. If it is bigger than this, it cannot be, because once again it would violate the fact that the strain is small, okay? So the material fails. So the only other option which is possible is that it is smaller than this. So if it is smaller than this, anyway its contributions would be higher order terms. So by adding certain higher order terms to asymptotically correct solution, you are not changing its order of magnitude in the analysis. So it still is asymptotically correct because you are just adding some spurious terms over there. But if you want to get higher order terms up to that level of the terms that you are adding because of the fact that W is small, then you have to collect all the terms of that order of magnitude contributing to the strain energy or to the total potential. So next what we will do is to restrict to class R beams. We will not look at class T and S beams, because even if we have to look at class T and S beams, the first or the initial step would once again be the same as what we are going to do for the class R beam. That is, basically take only the leading order terms. When we have class T and S beams, there will be certain additional terms that we have to take into account. That's it. So we will, in the remaining part of today's class, we will restrict to class R beams, and we will see how corrections can be added later. In other words, the higher order terms going for superior approximations or improved higher order approximations to the energy and therefore to the solution. Next, the 3D strain field. How is it related to the 1D strain field and warping? So again, this is something we have seen earlier in the previous example as well, just that the warping there was just a one-dimensional field only along the one direction, which is basically the out-of-plane warping. Now we have the in-plane warping within the cross-section as well. So, and in what we will do hereafter, we will have a contracted expression for gamma. We know that gamma is in a matrix form. It's a 3 by 3 matrix, but we know that it is a symmetric matrix. So in other words, it has 3 diagonal terms and 3 off-diagonal terms which are repeated. So therefore, for calculation purposes, either analytic or for that matter numerical, it's always prudent to instead express gamma instead of a 3 by 3 matrix. So we are giving a change of variable, change of definition of this particular variable gamma. Instead of a 3 by 3 matrix, we'll now talk about a 6 by 1 column matrix, which involves the 6 independent components of the capital gamma. Now, again, there is a difference which was also pointed out by Aditya when he presented for the plate. So a similar difference exists over here as well, that the way in which we are ordering these is slightly different from what it is done in conventional analysis, where typically they put gamma 11, gamma 22 and gamma 33 as the first 3 terms, which are the normals, normal strains, and then they put the 3 shear strains. But for certain reason, we put it in such a way that all the strains which are happening on the cross-sectional face, which is basically related to the one direction, we put it first, and the others which are happening within the cross-sectional coordinates, that is 2 and 3 directions, we put it later, and that helps to simplify a lot of things that we do later. So as you, in fact, you will see that within this slide itself, that what is the benefit of that. So that is the reason why we do that. But again, as long as we are consistent with this definition throughout the derivation, whatever result you get should be equivalent. The other quantity that we will introduce is another column matrix. This is a 3 by 1 column matrix consisting of the warping measures. And remember that these quantities W1, W2, W3 are along the small b basis. Similarly, your gammas are also an expansion of the strain tensor, which is basically the Jorman-Bioy-Cauchy strain tensor expanded along 2 bases, both of which are the small b bases, because we are dealing with Lagrangian strains, not with Eulerian strains. So remember that fact, that because whenever you write in terms of measure numbers or in terms of a matrix representation, that the basis in which you expand it out should be clearly mentioned, otherwise it could be very different from each other. Next, we define another quantity called O, or 0, with a subscript 3, which refers to just a 3 by 3 matrix consisting of zeros, and that will be used in the definition of some of the new variables that we will introduce. And now we define 4 matrix operators, and out of these, 2 are basically consisting of just either variables and or numerical values, and 2 are basically consisting of differential operators consisting of derivatives, partial derivatives with respect to x2 and x3. Okay, so now coming to the first one, it involves only the x2s, x3s apart from 1, and it is written in terms of the gamma, because all of these quantities are going to be used to have a compact notation or for the expression for gamma. The gamma, of course, is determined in exactly the same way as we did before, that is by determining the contravariant basis vectors for the undeformed configuration, the covariant basis vectors for the deformed configuration, juxtaposing them and then taking the dot products in a mixed basis. You have the expansions, but after expanding it, we can sort out those terms in each one of those expressions in such a way that we can lump them into 4 kinds of terms. One set of terms which depend on the 1D strains, that is basically your gamma 11 bar, kappa 1 bar, kappa 2 bar and kappa 3 bar, will be lumped into a term involving this operator. Then you will have terms which depend upon the warping, which will basically be these 3 terms. Again, all of these depend on the warping, but there is again a difference between those 3, and that's why we have 3 different kinds here. One is contribution purely because of the initial curvature and initial twist or pre-twist that you have in the beam. So if there were no pre-twist and if there were no initial curvatures, then the contribution from this particular term would go to 0. So leave that aside. Then you have again a contribution from warping because of the derivatives with respect to the cross-sectional coordinates, which you define as gamma subscript A, and A, remember, is also the term, is the variable that we are using to refer to the order of magnitude of the characteristic cross-sectional dimension. So that is a mnemonic to remember what this is associated with. And finally, you have a gamma subscript L. This R, of course, refers to the fact that it is associated with initial twists and curvatures. Now coming to L, these are associated with the derivatives of the warping with respect to the length coordinate, which is x1. So basically involving the w primes, w1 prime, w2 prime, w3 prime, etc. So that is why you have this gamma L. So once you have defined these 4 operators, 2 of which are differential operators and 2 of which are just operators which just multiply other matrices. Once you have those, in terms of these, you can see that after you find the expression for gamma in the same standard way, then you can sort out those terms such that you would now have an expression for gamma which basically looks like this. So it consists of 4 types of terms. The first type of term is this matrix multiplied with epsilon bar, where epsilon bar involves gamma 1 bar, kappa 1 bar, kappa 2 bar and kappa 3 bar. So gamma 1 bar multiplies this first column, kappa 1 bar multiplies this second, and kappa 2 bar and kappa 3 bar. So it's quite easy for you to see the first term, for example, gamma 1 will involve a contribution from the extensional strain of the reference curve, which is gamma 1 bar, and it would involve the contributions due to bending, which is basically kappa 2 bar multiplied by x3 and a kappa 3 bar multiplied with x2 with the appropriate sign. So that is basically what is contributing over there. So this particular term takes care of all the contributions which are coming from the 1D strains directly. The rest 3 terms that you have over here are all W dependent terms. So you have, this is W itself, this is again W, but the difference between them is this is due to initial twist and curvature, and this is due to even without the presence of initial twist and curvature, this would be present. And then finally W's which are having derivatives with respect to x1, and therefore its contribution is what is included in this. So typically the contributions of many of these terms would be fairly small in most situations, but basically we'll see what happens in specific cases a little later. But this is the overall classification that we are having over here, and in this the delta refers to the 3 by 3 identity matrix. The 0, 3 we already defined as a matrix of zeros. Yes, please.
So delta A as a
Gamma A.
Has a contribution from bending and other than this pre-twist and pre-bending.
Yeah.
Whatever bending takes place, right, sir?
No, gamma A is not dependent upon initial twist and curvature. It's purely dependent on the derivatives of the warping with respect to the cross-sectional coordinates, with respect to x2 and x3 everywhere.
In-plane warping contributions. In-plane warping contributions.
Also, it involves W1 as well. See, here there is W1, this is going to multiply W1, W2, W3. So your first column is going to multiply W1, second column is going to multiply W2, and third column is going to multiply W3. So you are going to have W1, 2 and W1, 3 contributing to the capital gamma 1, 2 and capital gamma 1, 3 terms. So basically the transverse shear terms. So that's where that particular contribution goes. So see, everything in general depends upon these 4 drivers, which is gamma 1 bar, kappa 2 bar and kappa 3 bar. These are the 4 classical measures which drive everything. But these terms are in terms of W, but eventually we will solve for W in terms of those epsilon bars only. Okay? So in other words, these are also contributions from epsilon bar, but in an indirect way through the warping, and typically smaller contributions. Whereas this is the direct contribution which is coming purely out of. So if you look at this, just multiplying this, your gamma 1 would be just small gamma 1 plus x3 into kappa 2 minus x2 into kappa 3. You would see that it is like a classical theory which involves basically an extension and the 2 bendings. So similarly, if you look at the next term, which is capital gamma 1, 2, would be just kappa 1 bar multiplied with minus x3 and kappa 1 bar multiplied with x2 as gamma 1 2 and gamma 1 3. So that's basically the shear, which is shear strain, which is caused by twisting the shaft, let us say. So it's just making a generalization of beam theory, column theory, and basically shaft theory. Okay, so torsion theory, extension theory, and the bending theory are all combined into a single matrix in the most simplest kind of beam formulations that you can have. But in general, you would see that you would not, if you had only this, that is only this term in the gamma, you would not have accuracies which are typically required in most engineering problems. So then you would see the need for bringing in these terms. Even when you don't have initial twist and curvature, these two terms are still going to be there, and you would see that in some situations they cause some large contributions which have to be taken into the account in the strain energy. But as I said, eventually all these W's would be solved in terms of the epsilon bars, so they are indirect contributions from the extension, twist and curvature coming through the warping, how the cross section deforms, changes its shape and size.
Right.
Whereas all of this happen primarily because of what happens to the reference line.
Actually, I was asking whether we can separate them as a contribution or separately, like this term for outer plane warping, this term for in-plane warping, not like that.
No. So all of them include the W as a column matrix, which includes the in-plane warping as well as the out-of-plane warping. So all these three terms involve that. Of course, you can still separate out by just looking at just the first column of each one of these. The first column would basically give the contribution from the out-of-plane warping, and the second and third columns would basically give you the contributions from the in-plane warping. So the above form of gamma that we see over there looks linear in epsilon bar, W and its derivatives, and so is the case. But eventually when you get the solution for W's, it is possible, of course we are restricting here to class R beams, in which case it remains like this. But when we go to class T and class S beams, the solutions for W can have nonlinear terms in the epsilon bar components, and therefore you would see that in such a situation it is also possible that these terms can contribute nonlinear terms as well. But again, this is something that we are restricting to only the leading order terms. It is possible that there might be additional terms which are having powers of W as well, which are left out of this kind of a thing, but that's something which is required more from an academic perspective of very higher order approximations to the theory, which are typically not significant for most engineering purposes. So this is what typically suffices. In fact, as I said, classical theory would not even bother about these three terms. It would leave that out, and just basically it's looking at just this contribution, whereas these are important as well, as we shall show. So now let's see how we can determine these constraints on the warping. We already discussed the need for this, that instead of just 3 measure numbers of R hat, we now have 4 quantities which are within epsilon bar and 3 quantities which are within your warping as components, and so we have 7 variables instead of 3, and therefore 4 are redundant. We need to express constraints. Again, I repeat that these constraints are not sacrosanct, just that the way you define them will dictate what is the meaning of the epsilon bar quantities, or rather what is the meaning of the UIs and the rotations which are involved. So let's see one way of doing this, determining the constraints on the warping. So the displacement field, as I already mentioned, is 4 times redundant, which implies that the number of constraints we need are 4, and all of them on the warping field, so that whatever you reproduce with an epsilon bar and W system would be the same as what would be reproduced if you just had the big R hat with just 3 measure numbers. The same thing has to be done. In other words, a uniqueness has to be established. So now the goal is to find those constraints, determine what those constraints could be, for example. One way of determining it is to just look at the expression we had for the strain in the previous slide, which is basically this. I've just interchange the first 2 terms, put the gamma epsilon alpha epsilon bar over here and put the gamma A W over there, because our focus is now going to be on this particular term. Amongst all the three terms which are contributing to warping, one is basically a higher order contribution because it involves a W prime, and one is something which is specific to beams which have initial twists and curvatures. So when you have a prismatic beam, for example, that will not occur at all. So the primary contribution for warping for all beams would basically be this particular term. So in other words, there is an important contribution coming from warping primarily because of this term, even in a straight prismatic beam. And in such situations, you would see that it contributes to the zeroth order approximation if gamma AW is not equal to 0. So in other words, if it equals to 0, anyway there is no contribution. If only in the situation where it is not equal to 0, it contributes to the approximation to the energy, right? So now let's repeat what gamma A is. So this is basically what it looks like. Now if this is the case, then we can also see what W should not be, because if W is a valid solution for the warping, then your gamma AW should not be equal to 0. But if gamma AW happens to be 0, then basically it means that it is not contributing to any strain at all. A warping which does not contribute to strain is not an acceptable warping, just like in your rigid body motion will not contribute to a strain, right? So similarly, a gamma AW which is equal to 0 is not an acceptable solution for W. This is what is an acceptable solution for W. So in other words, we will introduce another thing which just to distinguish between what is acceptable in yellow and what is not acceptable in W, just to show you the difference between that, and then we will reconcile the two together. So what we will do is now say that let's suppose gamma AW equal to 0. We know that this is basically 1, 2, 3, 4, 5, 6 row and 3 column matrix over here, and this of course multiplies W, which means that you're basically having 6 quantities corresponding to the 6 gammas, of course, the 6 components of the 3D strain. Now what would be an unacceptable W, or the blue W as you see here, would be something which when W multiplies this, it would go to 0. Of course the first term already goes to 0, it is quite obvious because all 3 terms of the matrix itself are 0. But if the other 5 rows also give basically a 0, that is no contribution to gamma and therefore no contribution to the strain energy, such a W is not acceptable to us. So to find the unacceptable warping functions W, all that we will do is we will solve a set of not 6 differential equations, because this becomes a trivial 0 equal to 0. So instead you have these 5. When I multiply these by W1, W2, W3, this equation, for example, this row would contribute a W1, comma 2 equal to 0. In other words, W1 is not a function of x2, okay? And similarly, when I take this differentiation, it means that W1, comma 3 is equal to 0, or W1 is not a function of x3 as well. So in other words, from these 2 equations, I can solve for W1 and say that it's a function only of x1. Now what does that mean physically? I'm saying that the warping W1, which is unacceptable, that's why I'm putting it in blue color. One of those unacceptable ways of warping would be for the out of plane warping to be a function only of x1. If it is a function only of x1, what would happen? Basically the cross section moves as a rigid body. So a rigid body translation, which I already accounted for in what I called as U1. So why should W1 account for that? It is basically repeating what has already been done, so that is not acceptable. Similarly, when we come to these, we'll see that this column multiplies W2 and this column multiplies W3. So here what it says is W2, comma 2 equal to 0, or in other words, W2 is a function only of x3, right? Similarly, what does this say? That W3 is a function only of x2, because W3, comma 3 equal to 0. So W2 is a function only of x3 and W3 is a function only of x2. Then when you go back and substitute that in this, here you get W2, comma 3 plus W3, comma 2 equal to 0. Now one is a function only of x3, the other is a function only of x2. For their sum to be equal to 0, both of them have to be constants. Okay, one constant, the other being the negative of the same constant. So that is the general solution which is possible. So when you expand that out, this is basically what happens, and you basically get this solution. Once again, I repeat that this is the blue color or poisonous color. So basically it's something which is unacceptable, whereas this is the acceptable. So we are saying what is not acceptable, so that then we can determine what is acceptable solution to warping. And once we know what is unacceptable, we'll be able to use that to get the constraints that we are looking for to avoid that 4 orders of redundancy that we have over here. So this is basically the solution. Already we saw that W1 is a C constant. Again, when we say constants here, we mean we are not taking x1 into account, because we are talking about a particular reference cross section where x1 is already fixed. So in general, of course, all your C1, C2, C3, C4 are functions of x1, arbitrary functions of x1. So that's what you have. But you see that W2 is a function only of x3, W3 is a function only of x2, and in such a way that W2, 3 is C4 minus C4, and W3, 2 is plus C4, so that this equation is satisfied as well with C4 minus C4 equal to 0. Okay, so that is satisfied as well, and of course a constant is still acceptable in each one of those terms. So this is the general solution you have when you have the derivatives or these differential equations solved for simultaneously. And there is a way to write this set in terms of the constants that you have determined. There are 4 constants, C1 to C4, and you have 3 warping measure numbers, W1 to W3, and these are unacceptable warping measure numbers, and that these two can be related in terms of a so-called kernel matrix, which is basically multiplying this column matrix of 4 by 1 to give another column matrix of basically 3 by 1. So that's basically what you have here. To find the xi ij in turns, choose each one of the Ci to be equal to 1 and the other 3 Ci's to be equal to 0. So it's quite easy to do that, and you can verify that indeed xi turns out to be this particular matrix, which is basically a 3 by 4 matrix, which when multiplies column matrix of C1, C2, C3, C4 will give you the unacceptable W1, W2 and W3 over here. So again, it's quite easy to see, because the C1 basically multiplies the first column. So you see C1 appears only in W1, therefore 1 there and zeros over here. And C2 appears only in W2, and therefore 1 here and the zeros over here. And C3 appears only over here, and therefore you see zeros for 1 and 2 and only in the third row over there. And then again C4 appears in 2 places. It does not appear in W1, therefore there is a 0 there, and its coefficient in these 2 cases is minus x3 and plus x2, which is what you have here as minus x3 and plus x2. So you can see that this is the kernel matrix, which is so-called, gives us null space modes, which you would be familiar from how to remove the rigid body modes from a finite element analysis program, for example. So in such situations also you deal with something like this, the so-called null space modes, which is what led us to this kernel matrix. Let's complete this aspect to it, is determining the constraints on the warping, because the reason why we determined the kernel matrix is to determine the constraints. That was our goal. So before we do that, we will introduce a particular notation, which I think we have introduced before, but this is something which we'll use quite frequently hereafter, which is basically these angular brackets. Anything which is contained within the angular brackets has to be integrated over the reference cross section. So if it's a rectangular cross section, for example, of width b and height h, with the origin at the center of the cross section, then what it would mean is an integral from minus b by 2 to plus b by 2 as far as dx2 is concerned, and minus h by 2 to plus h by 2 as far as dx3 is concerned. And that's basically kind of integration, but whatever the shape of the cross section, it's basically an integration over that domain. Next, the warping functions of interest, that is basically the yellow colored w's, now are orthogonal to the kernel matrix, because what is unacceptable will be orthogonal to what is acceptable. So that means that in turn, because the unacceptable w's are defined in terms of the kernel matrix xi, because remember that the unacceptable blue colored w is nothing but xi times c, where c involves a 4 by 1 column matrix of those constants, which are arbitrary, in fact arbitrary functions of x1. So it is clear that w has to be orthogonal to this kernel matrix xi, which means that you can put the equivalent constraint on the warping field as an integral over the cross section that W transpose times Xi is equal to 0, where W is of course the acceptable W. Okay, so that would, when written explicitly, would basically mean these 4 constraints. The first 3 would basically mean, of course, it's quite easy to see because this is what we got as Xi. So if you multiply W transpose, which is nothing but a row matrix now of W1, W2, W3, multiplying this particular thing, it's quite easy to see that the first 3, it's basically, if you look at the sub matrix, it's just like the identity matrix. So that just gives W1, W2 and W3 as 3 different equations. So the first set of equations is quite clear that basically the average Wi equal to 0. And again, the physical interpretation of that is also quite obvious, that we already saw what average W1 means. The average W2 basically means motion like this, which is again a rigid body like translation, and an average W3 basically means a translation in the vertical direction or in the x3 direction. So all that we are saying is that when we average it out, or integration divided by the area basically is nothing but the average. So because area is a finite number, therefore an integration over the area also means the same thing as talking about its average as well. So basically all that we are saying is that the average warping in all 3 directions are equal to 0, because if they were non-zero, they should actually have been part of the U1, U2, U3 respectively, which has already been determined, or rather to be determined using the 1D analysis. So you know that these means that the W doesn't contribute to the so-called 3 translations of rigid body like motion of the cross section. But remember that they are all in terms of the constant C1, C2, which are all functions of x1. So once again I stress that different cross sections can have different so-called rigid body like motions. That's why the qualification like is very important, because 2 different cross sections can have different rigid body like motion. So therefore the beam as a whole is not moving as a rigid body. There is still strain associated with it. So that's an important thing to remember. So
this result is independent of the choice of the reference line. Like if we choose shear center as our locus of the shear center as our reference line.
That's correct, yeah.
Or if we choose that centroid.
See, the choice of that will dictate on what is the specific meaning of the 1D variables, for example, and of what the meaning of the warping itself. But the constraint that you choose is something that is independent of that. Again, as I said, these are not sacrosanct constraints. This is just one way of defining it. This way of defining it, what it enables is basically that you have certain specific meanings for now your U1, U2, U3. So U1, U2, U3 get defined by this constraint, and in addition the choice of the reference coordinate. So your U is not singularly defined purely based on these constraints, but it is also defined based on the choice of the reference curve. In fact, we will see that the simplest case would be to choose, let's say, the centroids, and you would see the relationship between, let's say, the 1D displacements small u and the 3D displacements big U, which are functions of x1, x2, x3, and we will see that relationship, how the constraints affect it and how the choice of the reference axis also affects it. But this choice is independent of the choice of the reference axis, but as a combination, this choice of constraint and the choice of the reference axis together affect the meanings of the 1D variables.
Sir, in the previous slide, why are we solving for gamma A into W is equal to 0? That I could have, leading to the kernel matrix.
Why are we solving that? See, if it were equal to 0, then basically the warpings would not contribute to the strain, and therefore not to the strain energy.
There are other terms having warping, the gamma R, W and W.
Yeah, gamma R would come only when the initial twist and curvature were there. So this is something which has to be generally valid, which is valid even in the case of prismatic beams. Okay. On the other hand, the other one involves a W prime, which typically is a higher order contribution compared to the remaining terms. But there are situations like, for example, in class T beams, when the Saint Venant, what do you call that effect? The effect because of which the kappa 1 prime contributes to the energy, that basically comes due to the W prime term. Okay, but the primary contribution from the warping is from that gamma AW. So if that contributes as 0, it's pretty much saying that the that doesn't contribute anything, W doesn't contribute anything to the energy in the general situation. Okay.
Restrained warping.
Exactly, restrained warping, yeah. So let's go back to this. The second set of constraints, the first one already has 3 of them because I is equal to 1, 2 and 3, taking care of the 3 rigid body translations. The other one basically x2 times W3 minus x3 times W2 basically means that W doesn't contribute to the rigid body rotation of the cross section about T1. So basically it is a rotation which is already taken care of by kappa 1, which is basically the twist. Now that is not further contributed to by the warping is basically what that last thing says, and that of course comes from this last column over here where this multiplies W2 and this multiplies W3. So you have minus W2x3 and plus W3x2, which is what is over there. So next, the kernel for the strain energy function is a set of displacements causing zero strain or rigid body modes, which we already saw. In fact, that is why we called it the kernel matrix. This in turn implies 2 facts. One is that the 1D extension U1 and the bending displacement variables U alpha, which is basically U2 and U3 along x2 and x3, with easily identifiable geometric meanings correspond to the measure numbers in the small vi basis of the average displacements of the cross section. So the fact that your W1, W2 and W3 averaged over the cross section go to 0 in essence gives a meaning, though there is a catch in this, we'll come to that later, but basically the majority part of it, what it basically means is that once the warping average is equal to 0, then basically the corresponding u's, that is u1, u2, u3, small u's, which are functions only of x1, are nothing but the average displacements of the cross section. That has to be accounted for in that, because that is not being accounted for in the warping. On the other hand, if in this particular example we are taking the big T system instead of the big B system. Now in the big T system, once we know that the transverse shear is basically accounted for in the warping, right? So that transverse shear, remember, is actually also a rigid body like rotation because it is something which is happening over the cross section. Now you see there is no constraint basically dealing with the average rotation about the other 2 directions. There is only one rotation which is basically taken into account here, which is basically the rotation about the T1 direction, which is basically the contribution towards the twist, which is already taken into account. But the average rotations in the other 2 directions would in fact not be equal to 0 because you would have gamma 12 and gamma 13 coming out of it. But even in a situation where transverse shear is not important, recollect that we have only 4 orders of redundancy because instead of 3 quantities we have introduced 7. So only 4 constraints are in place, and those are the 4 constraints which are resulting over here. In other words, even in the most general case, in some way that 2 displacements U2 and U3 would be related to those rotations which are taking place about x2 and x3. So that is the reason why you don't get 6 constraints but only 4 constraints. The other reason, of course, is the order of redundancy is 4 and therefore only 4 constraints are there. The second aspect which is a fallout of this is because of this second set of constraint, or in other words the rotation related constraint, the fact that the 1D torsional rotation variable average rotation is nothing but the average rotation of the cross section about T1, which is approximately equal to the rotation about B1 in the case of small strains, which is what we are dealing with. But that's not an approximation that we are taking, it's just for physically visualizing that what is the meaning of that quantity, whether it is about T1 or B1. There will be a difference, but the difference will be very minor because of the fact that we are using small strains. Because remember that the angle between these quantities are of the order of magnitude of 2 gamma 12 and 2 gamma 13, which in turn are of the order of epsilon hat times A by L, or in other words typically 10 power minus 3 for most engineering problems. And therefore you see that whether you define it as about T1 or B1, it doesn't make too much of a difference. But strictly speaking, the way we have followed and the way we have introduced the constraints, it has to be average rotation about T1, which is what your theta 1 should be, and whose prime would be the leading contribution to your kappa 1. So kappa 1 would be theta 1 prime and some other terms which are also there. But basically the leading contribution to that would be the theta 1 prime, and it is that theta 1 which we are saying is that the average rotation of the cross section. So I think with this I'll probably stop today. Thursday I will not be here. So